Oh, yeah, that's right. Yeah, yeah. I forgot completely.
To make it easier for class.
Yeah.
And so the second day of class, I got here early and I said, oh, heck, I'll just start rearranging desks. And I got in here and it was like, no, we can't do that.
Yeah, I was pretty much, I would say, I would call it reprimand. I mean, it was not just a polite conversation. I was really reprimanded for that. So I was surprised, yeah, but nothing, it didn't go anything serious, but that tells you like what I felt was trivial is not. Say that again? No, this was a special circumstance. This was COVID, right? So for example, this room, we are how many? So many students couldn't be there in this room. So there was a limit of 5 students on this room. And I used my logic. So I said that, okay, so you have to maintain 6 feet distance. And I really made a geometry of this room and everyone can be 6 feet distance. And I said, yeah, we can fit in 8 people here. But already the university had said that there is 5 students. There was a written rule there. So forget about the 6 feet distance. There's a rule that there is 5 students. So I said, okay, 8 students as per the 6 feet protocol, and we will have it. But he said, no, you cannot. And that's because there is a bureaucracy from the top is telling that no, 5 is 5. In this room, it seems unreasonable. But imagine a classroom with 100 students. If you relax the condition, it will very quickly go out of control. So from the top administration, they just make it very strict. And when it comes to rooms like this, it seems unreasonable, but they're just maintaining a rule for the general crowd. So I got into that. I wouldn't say argument, I just did it, and who did it? So it was me, so it was not polite yet. But I got the point, and then I didn't extend it. So it was not bad, but still, I was surprised. So it might be the same thing. What sounds trivial to us, maybe not trivial at all.
Yeah, and they had the dots where someone had like pre-approved where everyone can sit. So yeah, I think like even if you rotate the desks, like these dots are the same distance apart, but that arrangement wasn't approved or whatever.
That's a good example. Yeah. And as I said, it sounds unreasonable to us in this room of 7 people. When you think of 200 people, it immediately makes sense. Of course, you cannot. It's like driving speed. Okay, your 40 miles per hour is a speed limit. What if you go 42? Is that breaking the rule or not? So, yeah, it's tricky.
At my school, if somebody had told me that I couldn't do something, I would make sure that I did that thing every day.
Well, you can get away with it, and I cannot. I think I give this example of Schwinger went from Harvard to UCLA. And in his biography, he says that, he will never show, he will be assigned committees and then he will not show up for the committee meetings. He just doesn't like committee meetings. It's Stringer, he can afford to do that. They're not going to fire him. But if a general guy does that, for example, if I say that I don't want to do this, I don't want to teach this course, okay, leave.
We had a professor that handed out the evaluations and basically said, I'm a full tenured professor, so you can say whatever you want.
Yeah, but there are some good things about all these things is that it is not that there is power play going on. At least in this university, there is a reasonably good union, and they do support your cause. You cannot just the power is distributed very well. So even if many people want to, they cannot do many things. Still, it is not a perfect thing still, but a lot of things gets taken care of. Like as I said, people cannot fire me very easily. But if there is a valid reason, of course, yes, but it may not be as trivial as it sounds. So which is good, which is like these things that I feel takes a lot of evolution to reach this stage. And often we underestimate how important this, I think we call it checks and balances, right? So it plays an important role, right? Which might be bureaucratic from a user's perspective, but very essential actually for the system to be stable. Like not for the system to run, but for the system to be stable. Right? So. Missing someone? Everyone's here. In 2 minutes break.
So to start out, you're gonna recap everything we did in the first 8 weeks and then.
No.
Okay.
Simple. I was actually, when you started the sentence, you're going to recap, I was thinking you're going to say from the last lecture, because we left it and I want to start from there. But what I decided was, no, I was not even going to do that because I want to conserve a little bit of time. There's a chance that it might overflow. So I think that just those equations are good enough. We'll see. So there are a couple of homeworks which I say can be made due on Thursday. So homework 5 and 6, let's say. It was one of that was on March 15. Let's make it due. Unless you can do it itself. So 2 weeks. Yeah, so today we want to do something very straightforward, but or at least I want to begin with something very straightforward, and I will use a heavy machinery to do that. But the purpose is that we will do it, we'll extend it to a slightly more general scenario, and then you will see why the machinery is being used. So let's, we want to solve, so this topic we can call normal modes. So this has to do with, we have a Lagrangian, you solve for the Lagrangian, you get a differential equation. Most of the time, most of the systems are nonlinear, but in the small angle approximation, which means to say that whatever variable you're choosing is small relative to something else. And then there is a linear regime there. And in that case, you get differential equations. And the differential equation might look like this. Like this is one of the simplest differential equations you can get. Like the theta omega 1 squared. Theta, and theta is a function of time. So this is second derivative is equal to 0. Right? That theta could be a variable representing a generalized coordinate or a dynamical variable, which describes the problem. What does the system describe? So, name for the system. You see this differential equation, what will you say?
It's a harmonic oscillator.
It's a harmonic oscillator, right? And it has a it will oscillate with frequency omega 1, right? So that's called a mode, like in music, you say tone. I think that's the with what frequency or what frequency is the sound having. If there is a single frequency, then I think you call it a tone. Is that correct? So then you will say it is a tone. So this particular oscillator could have oscillated at any frequency, but this specifies that given a choice, it will oscillate at that particular frequency. And that's what we mean by mode. So the statement would be that this system, whatever the system is describing, has a normal mode of omega 1. And very soon we want to have two such modes, and then we want to talk about linear combinations of this, or what would be the mode associated with it. But let's see what is the solution for this. And what is the solution for this? Theta as a function of t. What is the general solution? Sine and cosine. Correct. You would say there are some constants a, let's say cosine omega 1t plus b sine of omega 1t. Usually, this equation does not describe the problem completely. You have to give initial conditions. So this equation plus initial condition, say theta of 0 is equal to 0 plus theta dot of 0, that's a velocity, right? If you give me the position and velocity of a spacecraft today, we can predict it 6 months down the line that where it will fall on Mars. And this could be, let's say, initial condition is omega 0. Or let's call it theta. No, it's theta dot, right? So it's good to call it omega. This is angular speed. And that's some arbitrary parameter in there. Once you have these two initial conditions with the differential equation, you immediately say that, oh, this implies that. So this implies that if theta 0 is equal to 0, then A has to be equal to 0. And plus, right? Theta dot is equal to 0. So this becomes a sine, this becomes a cosine. So B will be equal to omega naught over omega 1. Right? So that's it. This is a homework exercise or quiz, right? Yeah. Show that this is actually true. It should be me. And that tells you that the solution actually is A0, B is sine omega t, so it is omega naught over omega 1 times sine omega 1t. Right, that's it. A standard problem you would do. Given a differential equation plus initial condition, you reach the solution. Right. Let's do this in a complicated or using, I say, heavy machinery, right? Even though this is straightforward, we will do it in a complicated way, which will be useful to get an idea of how to do this in a slightly more general situation or exactly what is happening with user field. Okay, so let's use Fourier transform for this purpose. So Fourier transform. So Fourier transform is, let's say, any function of time in frequency space, or Fourier transform of this will be pi e raised to minus I omega t times theta of omega. These two are not the same functions, even though I use the same letter. It should be a new parameter, let's say theta tilde or something. But for convenience, I'll just drop the tilde from this point on. But whenever you see an omega in it, the context should tell you whether it's a omega dependence or t dependence. If it's an omega dependence, it's the Fourier transform of the theta function. If you want the inverse of this, just for completeness, this is equal to minus infinity plus infinity dt raised to I omega t, theta of t. So the idea is clear that if you're looking for this function and you find the frequency function, then if you can complete this integral, you actually know the solution. Correct? And so we will look for, the idea would be that instead of solving for t in the position of a time space, we will work in the frequency space, and frequency space, this equation, which is a differential equation, will become an algebraic equation. Algebraic equation means a polynomial equation, and it will become easier. Solve it in the frequency space, and then we have to go back. So the price will be in the integrals, and it will turn out that sometimes these integrals are straightforward. Okay, so we are interested in this equation. Substitute this in there. What's the time derivative of theta of t? It hits, when on the right side, it hits only on the exponential. It basically brings down an omega. So this is a minus I omega. Q pi and exponential of minus I omega t and minus I omega theta omega. So what it has done is that when you look at this, wherever there is a time derivative, it brings in and minus I omega as far as the frequency space goes. So one realizes that you don't have to really operate this as a complete differential equation. In the frequency space, a derivative is basically minus I times frequency. In the frequency space means this is your frequency space. Right? Strip this expression off the integral, whatever is remaining is the Fourier transform of this derivative of the function, and you realize that, oh, I have the original Fourier transform multiplied with a minus I omega, and that's the derivative. And if that's the case, then I will immediately write this equation down in the frequency space this time. Right? The frequency space, the equation will be my second derivative will be minus I omega squared, two of them, and theta of omega this time, plus omega 1 squared, theta of omega is equal to 0. And that can be written as minus is plus, minus or minus 1 squared is plus, I squared is minus 1. So this is nothing but minus of omega squared minus omega 1 squared times theta is equal to 0. It should be written that it is theta of omega. Like that. So that's no more a differential equation, right? We are interested in solving for theta in the frequency space, that is theta of omega, and that satisfies this equation. What's the solution for theta of omega if that's the equation you have? What can you say about theta of omega? If something satisfies this, what can you say about theta of omega?
It's 0 unless omega equals omega 1.
Exactly, right? So you can immediately say that theta of omega is equal to, because you need the product of these two to be 0. If this is not 0, you surely know that this has to be 0. So it is equal to 0 if omega squared is not equal to omega 1 squared. And then, of course, it leads to one point is left out. And you say that if omega squared is equal to omega 1 squared. What is, if omega squared is equal to omega 1 squared, what should the theta frequency function be? Anything, actually. As far as this is satisfied, it could be anything. So let's call it a of some arbitrary function, a of omega. Right? And it's zero everywhere else. So it is basically, it's a point, it's a constant in principle. It's a A. It's not really a function of omega. Is that clear? So that's good enough. And we don't have to do anything, and we can use this if or condition and proceed. But this looks very much like a delta function. So as well, say that this is maybe one can say that your omega is actually function. Actually, let me do one more thing. That is this factor of 2 pi, which will float around. So it's an arbitrary function. So let me put a 2 pi there. It will cancel out later on. It's just for convenience. So this is equal to 2 pi times A of omega and delta function of omega square minus omega 1 square. Because delta function has this feature that if this is 0 every time, right? So this is automatically 0 because of this property. And whenever that is not 0, this is arbitrary. Just that it shouldn't be infinity itself, or it shouldn't be. Yeah, it shouldn't be infinity. That is the only requirement to put that. It shouldn't be some growing function which touches infinity. Yes. So that should be okay. Any questions at this stage? Very straightforward. Just that we are doing it in a roundabout way to get the same solution. Okay. So if that is the case, now I have this. Let me process this a little bit more. If you have a delta function of a single variable, it's straightforward. Whenever you have a delta function of more than one variable, so maybe yeah, so maybe a quiz. Show that. Or let's say identity, right? I will use an identity, but I would say maybe prove it, right? But you can use the results out there. Okay? So delta function of, let's say, some y of x, right? A polynomial of x. So there is a function here. For example, it's not linear, it is square or cube, or so it's polynomial function. This is equal to let me make it simple. I don't think we will require that figure. Simple. Let's say. So this is x minus a1 times x minus a2 and so on. Or let's say x minus an. I think it might be easier to do this one. Whatever I wrote earlier, any polynomial can be written in terms of roots. So it's sort of the same thing, but probably less abstract than this. Oh, I forgot to move it. So that's equal to delta of x minus a1 over whatever is this quantity here. Is x minus a2, multiply everything x minus an, and evaluate it at x equal to a1. Notice what I did, I removed the a1 contribution, and the product of everything else I evaluated at a1. That's a coefficient that comes in. Next one will be, just for demonstration, a2 over x minus a1, x minus a3, and so on. Is that clear? And you a2, and then you evaluate this at x equal to a2, and so on. Is that clear what I said? Okay. Any questions on that?
For the second term, it has x minus a1 on the denominator.
X minus a1 times the a2 is missing. In this whole set, a2 is missing.
Right.
In the next third one, a3 is missing. and so on. Okay. I got lazy because there's no space. So example would be delta of x omega square minus omega 1 square, which is delta of omega minus omega 1 times omega plus omega 1. That's equal to delta of omega minus omega 1 over omega plus omega 1. Take a magnitude, that's important, and evaluate this at omega equal to omega 1. And plus delta of omega plus omega 1 divided by omega minus omega 1. Evaluate this at omega equal to minus, which is the same as 2 omega 1 magnitude plus 2 times omega 1 again magnitude. That clear? So if that's the case, our function in the frequency space is trivial function actually, 0 everywhere, and there is constant in front, but we are writing it in a reasonably complicated manner, and that is so that's 2 pi, no, a, yeah, 2 pi times a of omega 1 if you want, divided by 2 times omega 1 delta of omega minus omega 1 plus 2 pi times a of minus omega 1 over 2 times. Again, don't lose contact with the simplicity of the solution. It's just we're going around in a roundabout way and we will reach exactly the same place. The solution is not going to change. But the claim is that this will have more insight in the next problem that we discuss. Okay. You can as well call this, now that we have reached this stage, let's call this 2 pi a prime omega 1. This was arbitrary anyway. Make it, this whole thing is a prime. So this whole thing is a prime. This is delta of omega minus omega 1 plus 2 pi a prime minus omega 1. Actually, let me call it B. So this is a new parameter, so let me as well call it B of B prime. To connect with this A and B's. So that also. Because arbitrary, why not redefine it? Okay. You're still in the frequency space. This just tells us that whatever this function is, only when omega is equal to omega 1, this survives, otherwise it's 0. That's the only point. Okay, but what about in the position, in the time space, you have to put this inside the integral. So minus infinity to plus infinity, 2 pi exponential minus I omega t, and substitute that in this piece here. So it is 2 pi e of, I should also point out that this was an a of omega, right? And I replaced it with omega 1. That's okay because delta function is evaluated at omega 1. It survives only at omega 1. Okay, so it's okay to do that. But if you feel completely comfortable immediately, you can even say A of omega. It's okay. But the moment you multiply it with the delta function, you can restrict that. It survives only there. So that's an omega 1, and that is delta of omega minus omega 1 plus this prime, right? 2 pi b prime omega 1 delta of omega plus. That's a delta function. You can solve this immediately. Right? Integral of a delta function is replaced omega is equal to omega 1 in the integral. 2 pi cancels out. And you learn that a prime of omega 1 exponential minus I omega t plus b prime of omega 1. And that's your statement here, except that this is written in cosine and sines. Exponentials are cosines and sines. If you want to see that more explicitly, this is a prime omega 1 plus b prime omega 1 times cosine omega t plus minus of a prime omega 1 plus b prime sine. Call this A double prime. A double prime, call this B double prime, and you learn that this is A double prime of cosine omega 1 t plus B double prime. And that's your solution, which you have just directly checked by substituting. Yes.
Isn't the B prime minus omega 1? On the next line up.
Oh, here. Notice when I was redefining this, I defined it to be a function of omega 1.
Okay.
It doesn't matter if it is
Okay,
minus.
okay, that's not omega.
Yeah, if you stay with minus omega 1, that's perfectly fine. You just be consistent. Okay, so there's nothing wrong here. But I can see that since this was minus omega 1, why it would have been slightly more natural to put it like that. Is that clear? So that's it gives in this way of doing, instead of, so this was guessing, right? We can check that, if you substitute cosine omega t, you can do that sine omega t does that, or you can solve the differential equation directly using what's it? Again, you will substitute by exponentials and do that. So we are sort of knowing the solution and getting it. But here, in a sense, you would go to Fourier space and an algebraic equation gives. It's the basic same idea, but it gives you a procedure to do this. And now we want to use this procedure in a slightly more coupled situation. Okay? Any questions at this stage? Okay, so if there are no questions, now what we want to do is there are two harmonic oscillators. Let's theta 1. This is T actually. T is equal to 0. So that's one harmonic oscillator. A second harmonic oscillator plus omega 2 square. 2 T is equal to 0. And there is nothing great or nothing more any more complicated than what we have already done. These are two harmonic oscillators completely independent of each other. If we know the solution of one, the second one will have exactly the same solution, except we have to replace whatever omega 1 is with omega 2. So nothing great in that, but we want to now couple this. We want to slightly couple this. So let's say this is what was our problem? So the last time we came up with an equation at the end. So it was alpha over beta, theta 1, theta 2, double dot plus t plus beta And if you think of alpha and beta to be small, like, or this alpha over beta and beta to be small, what we are saying is that this is oscillating, the first pendulum is oscillating as it was earlier, but this is going to affect that in a slight manner. If alpha and beta are small, this will slightly perturb this. And once this perturbs this, this will perturb that. So there is a coupling between the two harmonic oscillators. And that's a classic double pendulum. Double pendulum is coupled very strongly whenever you see that as a complete setup. But if it's a small angle approximation, the coupling could be very tiny. And then you will see most of the earlier oscillations in there. And this is a perturbation too. And that's the motion we want to consider. And notice there are second derivatives. And the point is, can we use our techniques that we just now developed to solve this? That's what we want to do. So the idea is same idea, right? The first thing you do is all the derivatives with omega, right? So all the derivatives replaced with minus I omega. As a square of them, so that's minus omega square. So this becomes minus omega square minus omega 1 square times theta 1. This time it is in frequency space, right? Plus, actually minus because there's a second derivative again showing up. So that's minus alpha over beta omega square theta 2 of omega now. That's equal to 0. And the second equation, very similarly, is minus omega square minus omega 2 square times theta 2 of omega. And this is minus beta omega square theta 2. That's clearly a coupled equation. Yes. Oh, yes. Okay. So basically replace it. That's the omega. Wherever there's a second derivative, it gives you minus omega square. And the only manipulation I did is I took out the minus sign so that I can write it. So,
Isn't the second of theta in the second line
theta 1.
theta 1?
Yes. Thank you. Yes. Yes. So let's write it in a slide. So this is rewriting basically. Or better. Let's keep it in this form so that we can compare. So take it to the other side of theta 2 omega. And theta 2 omega itself is same thing. So theta 1, theta 2 affects theta 1 affects theta 2, properly coupled. And these are the processes that give you resonance effect and beats. All that involves these motions. Okay. So what did we do next? We want to solve this, correct? So we want to get an equation like this and solve it, but this is not yet in that form. This is coupled, right? So substitute one in the other. And if theta 1 is theta 2 is this, substitute one in the other. And for that, what I do is I'll multiply by omega square minus omega 2 square from the left side. So this becomes omega square minus omega 2 square. Omega square minus omega 1 square was already existing. And when I multiply this on the right side, so I multiply with a minus of that, so this becomes a plus. This I can replace this, beta cancels, alpha omega is 4. And theta 1 omega. So I have an equation now. So this is omega raised to 4. There's a omega raised to 4 here also. That is 1 minus alpha omega raised to 4 minus of omega 1 square plus omega 2 square times omega square and plus omega 1 square omega 2 square omega 1 omega is equal to 0. That's very much like this equation, except now it's a fourth order polynomial instead of a second order polynomial. Very similar. And what about theta 2? Like if I know theta 1 from this equation, I can get theta 2 using this particular equation. I just have to multiply it, right? But we'll come back to that. If we have this has 4 solutions, correct? This is a quadratic equation. So omega square is equal to minus of this. So it's omega 1 square plus omega 2 square plus or minus of the root square minus of 4 times 1 minus alpha. 1 square omega 2 square divided by 2 times 1 minus alpha. In fact, 4 solutions, so it is plus or minus of square root. Okay. So 4 solutions in the sense this plus or minus and this plus or minus alternated, and you get omega plus minus. So there are 4 solutions here. Let me call this. I don't want to say this. So this is equal to plus or minus of omega A or B, right? The plus. What do you say this? Without this plus minus, I call it omega A or omega B with the plus minus sign. Should I define this? Omega A, so that there is no confusion. Right. Minus 4 times 1 minus alpha, omega 1 square, omega 2 square. 2 times 1 minus alpha. And yeah, why not call it plus minus, but plus and minus. Then omega plus is this, omega minus is this, and the 4 eigenvalues are plus or minus omega plus minus. Right? So the 4, so this equation then can be written as omega minus omega plus, omega plus, omega plus, omega minus omega minus, and omega plus. Okay. Efficiency. So these are your 4 solutions, or these are the 4 solutions. Whenever you know the roots of a polynomial, you can write it as a product of x minus a1, x minus a2, x minus. So these are the 4 solutions. Omega minus omega plus, that's your 4. Maybe I had to pull out an omega, 1 minus alpha, but 1 minus alpha, okay, that's 0. Maybe if it at all helps, but that's okay because 1 minus alpha it's equal to 0. So Questions? Don't like it. Or it's not comfortable. Whatever I've done is, so if I have ax squared plus bx plus c, this can be written as a times x minus, that's a root 1 times x minus r2. And why is that? So that's the same as a times x squared minus r1 plus r2 times x plus r1 r2. And that's the same as ax squared minus a times r1 plus r2 times x plus a times r1 r2. What are the two solutions for this quadratic equation, or let's say it's the same thing, correct? So here it is A, so B is A times R1 plus R2, and C is equal to A times R1 R2. What was I trying to do? I was trying to show that this R1 and R2 actually are the, if I write this in terms of this, these are actually the roots. So get the roots there. So x is equal to minus b plus or minus b squared minus 4ac over 2 times a. If you add these two roots, so this is your R1 and R2, right? So that's your R1. And that's your R2. It's just a demonstration for double. So R1 plus R2 is indeed minus B over A. When you add these two cancel out and B over A. And if you were to multiply R1 times R2, this is A plus B, A minus B. So you can actually do A square minus B square. So it is B square minus of B square minus 4AC divided by 4A square. Right? And I wanted to show this is C, right? C over A. So B square cancels out. So it is 4AC over 4A squared. So that's C over A. So hopefully that is slightly more convincing. This is just a demonstration that for two quadratic equation can be written as the product of x minus roots. So this is in general true for anytime. Anytime you have, if you know the roots, you know the polynomial in a sense, which is remarkable. I mean, if you think about it, you have a function, right? So you have these functions. If you know these points, you know the function. It's kind of a remarkable statement. That sounds okay, but whatever. That's all review for you guys of very basic things, I suppose. In a sense, okay. If we have this equation, what we did here was that then we said, oh, so now we are in this state. We have, if this is true, then that has to be true. For condition, right? If this is neither of this is 0, then that is equal to 0. Otherwise, one of this has to be 0. And if this is equal to omega minus, then this is, or any one of them is 0, then you know that that's not the case. So you can, in general, write theta of omega, theta 1 of omega if you want. Could be, and again, I'm not going to use the fact that in general, we have to go through this identity, right? So there are 4 identities. First, you write this as a delta function, and then maybe write it. Yes. So you have this A of omega, right? And then there's a delta function of omega plus omega plus and omega minus omega minus. And I can go through this whole process of actually evaluating the derivative and so on. But I don't care because eventually whatever the derivatives came up, I anyway redefined it to be a constant. So I don't care as far as I capture all these delta functions. So I say that the solution will be equal to some A of omega plus. We can even leave it, A of omega plus times delta of omega minus omega plus this time B of omega plus times delta of omega plus C of omega minus of delta of omega minus plus D omega minus times delta of omega plus. Any questions on that? Once I know this, I should have written 2 pi, right? Yeah, anyway, this was primes, right? B primes. And put a 2 pi there. 2 pi there. 2 pi. Since it was arbitrary after those coefficients, I just redefined. Like that was the whole idea of doing that simple exercise earlier, so that I can hand wave it here. Because it's more tedious to do it here. It's just here, it's bookkeeping.
Use the same identity before.
Yes, same identity. You have to go through all the steps. But notice if I went through all the steps, I anyway at the last point said that I will redefine it as a prime. I said, I don't want to go through this anyway. I'm going to kill all that in the new definition. So that's what you get in the new definition. Now do the Fourier transform. If I substitute it in the Fourier transform, what it does is that it brings out the exponentials in the right form. That's it. So this is equal to A. So now theta 1 of t is A prime of omega plus exponential of minus I omega plus t plus B prime of omega plus of because it's constant. That was what Rob was saying. If it was an omega, then I would put it in as a minus, but I define it as omega plus. So this is exponential of I omega plus t plus C prime of omega minus exponential of minus I omega minus t plus D prime of omega minus of exponential of I omega t. And from this point again, we did this cosine and sine identities. We can do that immediately and say this is A double prime of cosine. Let's write cosine first. Omega plus t plus B double prime sine of omega plus t plus C double prime cosine of omega minus t plus B double prime. So when this is all showing the details, for example, if this is the crux here, right? 3-sentence solution. Instead of doing all this, you immediately say that whenever I get this solution, I'm going to write this as A and B. Same thing, whenever you get 2 coupled equations, find the modes first, solve this polynomial equation. There are 2 roots you get, and each one gets a cosine and a sine. Like these are called the normal modes. Omega plus and omega minus are the normal modes. And instead of 1 mode, you have 2 such modes. That's the, you can, whenever next time if you're doing a homework problem for me or for that matter for anyone, you can start from here. It's perfectly fine. Okay. And then you should know how to get omega plus and minus. Exactly the same way as once you're given this equation. In what spirit do you write this? Unless it's a one is expecting that you prove that, you can directly write that solution and go. Same thing here. Once you know that these are the differential equations, you can start from here as far as you know how to get omega plus. But then we are still left out. There are four values you need to find, right? So you need to have four boundary conditions, and it's not very obvious. What about theta 2? Like, what do you tell for theta 2? So let's talk about that for a minute. This crossed. So if I know theta 1, what is theta 2? I can go back to the original equation to get theta 2. So theta 2 of omega is equal to actually minus beta omega square of over omega square minus omega 2 square. That's theta 1 of omega. Oh. Okay, for reminding. Notice this is in the Fourier space, it's in the frequency space. So this is what you will have here. That's the same as so let me define something. So this is equal to yeah, let's just do it mechanically. And theta 1 we know is a which 2 pi prime omega plus plus 2 pi b prime plus and then you ask, okay, what happens to theta 2 as a function of time? I would substitute this in here, right? I would substitute in this for the Fourier transform, and each of this is a delta function integral. It contributes by replacing omega. Earlier it was straightforward because there was no omega, so there was only omega in exponential. It was straightforward. But now the coefficient has an omega dependence, so I have to take care of that. So this gives you minus beta omega plus square divided by omega plus square minus omega 2 square. And that's a prime omega plus e raised to minus I omega plus t plus d prime omega plus. That's the first two terms, but then there are two more terms. In the next two terms, I replace it with omega minus, right? So this is same coefficient But now omega plus is replaced with minus. It's usual to call this as some gamma plus. This is gamma minus, right? That's your, this is your gamma, right? Gamma is evaluated from here, which comes from your equation here. So the second solution is good to say it is gamma plus of a double prime cosine omega plus t plus the double prime sine of omega plus t plus gamma minus. Okay. So summary is that, so that's yours. So I'm going to erase this. Summary is that, so summary, whenever you have coupled differential equations, find the modes, go to Fourier space, go to Fourier space, which is done basically by replacing d by dt to minus I omega. Find normal modes and find normal modes. If it's a two-dimensional, two-parameter problem, then there are two modes, and the solution will be eta 1 of a cosine omega plus t, these are the modes, plus b sine omega plus t, plus c omega minus t plus d sine. And the second function is gamma, gamma plus. Yes. Thank you. Yeah. Thank you. Oh, and in the last 5 minutes, let's do a simple example, right? Where we solve for A, B, and C, A, B, C, and D. And you would see this in various forms. Once you understand that the details of what each piece is doing, this is mostly a procedure, and you find easier ways of doing this. For example, you can write this as a matrix, find the characteristic equation instead of finding that polynomial equation. You will see it as a characteristic equation, and there are various ways of doing it, which is more elegant. But this is broadly, the idea remains the same. This is why we are doing it, and that's why you get this. Especially to motivate these coefficients will be harder any other way. Why will be multiplied with Otherwise, you can also put in new parameters in here and solve for those parameters going back to the equation. That equation also has to be satisfied, right? So that's another way of doing it. So, but this gives you an idea of how to do that. So let's do lastly, let's do solve this for the initial conditions. So let's say example. The example, say initial conditions, theta 1, 0 is equal to 0. This is like thinking of a double pendulum, right? So you have a double pendulum which you start as, so that's your one pendulum, that's your second pendulum, right? That's your 1, that's your 2. Let's say theta 1, 0 is 0, theta 2, 0 is 0. Theta 3, no, theta 1 dot 0 is equal to 0. I don't kick this, I kick the second one. Right? So the initial condition is that I'm just going to hit the bottom of the rest everything stays 0. So that's your omega 2, let's say, or omega 0. That's your initial condition. How do you get this? So put that in the equation, right? So it is 0 is equal to A, right? B doesn't contribute plus C. That's your first equation. And second equation is 0, no, theta 2 is that's also 0. 0 is equal to gamma plus A and plus gamma minus C. Immediately you get A is equal to or C, like that's right, in terms of AC is equal to minus A. So this implies that gamma plus minus of gamma minus times A is equal to 0. And gamma plus minus gamma minus probably is not 0. This probably implies that A is 0. Check this. Quiz. So I'll show that A is equal to 0. But we have to go theta 1 also, right? The derivative also. Do this derivative whenever you take the derivative of cosine, omega plus goes in the front and this becomes a sine, right? And sine function is anyway 0. So I'm going to do this in my head. So this is theta 1, 0 is equal to 0 implies, right? Theta 2, 0 is equal to 0 implies this. And next is theta 1 dot 0 is equal to 0 implies. Move. That's equal to 0 times. When I take the derivative, that becomes a sine. I don't care. So it is omega plus times B. And this will be plus omega minus times D. That's equal to 0. So you learn that D is equal to omega plus over omega minus times B. That's one relation. And finally, something that is not 0 is theta 2 dot 0 is equal to omega naught. But everything is 0. It's trivial. That's equal to omega naught is equal to, here again it is plus times omega plus times B and again the same thing, plus gamma minus omega minus times D is equal to omega naught. That's your two linear solutions. If you want, like, we can solve this in the following way. Omega plus D. So omega naught. So B will be equal to B will be equal to replace this omega naught here, 0, 0 goes to minus minus of omega naught times omega minus divided by minus of gamma plus times oops. Okay. Check this. I have this doing it in my head. D similarly is equal to omega plus that's probably minus did it in a rush, so could be mistakes, but that gives you an idea of how to go about this. It's mostly algebra. Everything is algebra, but it gives you an idea. Every step is kind of implied by the first earlier step. That's all. And this has, of course, very important applications. Most of the problems can be written as uncoupled equations, and then you introduce the coupling, and you can get the dynamics of a more complicated system in terms of simpler system. The most classic two-body example is a laser problem where you have a two-level atom. Light comes and interacts with it. Light is independent, atom is independent. Introduce a coupling, and they do something. And that's usually that. Okay, I'll stop here, and next time we'll go back to the Lagrangian and do the boundary points. The time variations at the boundaries. What do they mean? You find the relations. Okay, thank you.